Hello everybody. This is video one in a series of videos that are going to be about optimization problems in calculus. If you go into Schoology today, which is Monday the 21st, you will find a document in there called Optimization Stations, and it has 4 stations where optimization problems are in categories. So what I want to do in these videos is talk to you about the types of optimization problems that we see kind of one type at a time, so that the hope will be when you see these types, you will recognize them and therefore have an entry into the problem. So there are 4 stations. The one I want to start with today is Station 2, which I call the constructing problems. It's where they're asking you to build something. So there are also problems that we did an example of the other day, the 2D to 3D, where we were folding up the sides of a box. I'll make another video about those. There's constructing in 2D only, which are kind of interesting. And then there's my favorite ones, the enclosure problems, where you're building fences and stuff like that. That's Station 4. So today, though, I want to focus on Station 2, which is constructing. We see lots of problems like this. So again, just like we talked about the other day, anytime you have an optimization problem, there's going to be something that you're trying to optimize. There's going to be something that you're trying to find the most or the least of, the maximum or the minimum. So you're going to see these extreme words. In this problem, we see what dimensions will use the least material. So I know that I'm minimizing. But in the end, minimizing versus maximizing, it's the same process, right? We're going to find an equation, we're going to take the derivative, we're going to set it equal to 0. It doesn't matter if we're looking for a max or a min, that equation is going to give us both things. And then it's up to us to look at the restrictions of the problem and figure out which one is our min, which one is our max. Okay, so in this problem, it says you have been asked to design a 1-liter oil can shaped like a right circular cylinder. In case you're wondering, that is the fancy name for what we affectionately refer to as a cylinder. What dimensions will use the least material? So we have to do a little translation here. When it comes to optimization, I see the word least, but they say the least material. So it's up to us to think about what quantity we're trying to optimize here. So in order to use the least material, I need to think about how my can is built, right? In order to build this can, I need to build a wall around the outside. I need to have a top and I need to have a bottom. Okay, so if I want to use the least material as possible, assuming that the thickness of the can is standard, we're not going to go there. I need to find an equation for the surface area of this can, right? Because that's going to be how much material gets used, right? Based on the height and the circumference of this can, it'll use a different amount of material. A very tall, thin can is going to use a different amount of material than a very short, fat can. And we want calculus to help us figure out what that is. So the thing that I'm optimizing here is going to be surface area. So we'll have to write an equation for the surface area of that cylinder. Okay. We also need to look into the problem and find our restriction. Sometimes I call it a restriction, sometimes I call it a limitation. Because again, and this is really extreme and kind of silly, but if you just say to me, what dimensions will use the least material? My answer is no dimensions. I just won't build the can. How do you like that? So they have to give you some restriction. They have to give you some criteria like, okay, you need to use the least material, but your can has to fit this criteria. You have to meet this restriction. And in this case, the restriction they gave us was that the can has to be a 1-liter can. 1 liter is volume. So my restriction here is going to be the volume of the can. Now I want you to be careful with units here. You can stick with liters, but when you start talking in liters, your units on your dimensions are going to be, I believe, decimeters, which I'm not playing with. So instead of using a liter, I know that a liter is 1,000 milliliters. And the reason I'm going to use that is because if I use milliliters here, then I know for a fact that all my dimensions on my can are going to be in terms of centimeters. And that I don't want to mess up on units in these problems, because if there's a point for units, that's the last thing we want to miss. Okay, so I have this restriction that volume is going to be equal to 1,000 milliliters. So I need two equations for this can. I need an equation for its volume that I know is going to be equal to 1,000, and I need an equation for its surface area. That's the one I'm going to end up taking the derivative of. Okay, so let's start with volume. Let's start with our restriction. If I need the volume of this can, that's going to be the whole area of the top of the can multiplied by the height of the can. So the first thing I'm going to do is identify some dimensions on here. So here's the radius of my can, which is going to be important. And then here's the height of my can, which will be important to us as well in both equations. Okay. So if I want the volume of my can, that's going to be, oh, I'm already messing up. Volume. Okay, volume, that's going to be the area of the top, so that's my pi r squared, times the height of the can, so times height. That has to be equal to 1,000. Right? This is my restriction. Okay? If I take the radius, square it, multiply by height, multiply by pi, it better darn well come out to 1,000. Otherwise, I don't have a can that has a volume of 1,000. All right. Now, I want to optimize my surface area. So this is where we're going to be taking our derivative, right? This is where the calculus comes in, the optimization equation. So I need an equation for surface area. So the surface area of this can is really is made up of three surfaces, right? I have the lid, I have the bottom of the can. Those are both pi r squareds, right? So I have two pi r squareds. I have a lid, which is a pi r squared. I have a bottom, which is a pi r squared. And then I have the side wall. Okay, so there's my lid and my bottom. I need this side wall. And one of the ways that you can figure out the best way to figure out the area of this side wall is to think of it as, instead of a round surface, think about coming in here, slicing it, and then unfolding it. If you do that, if you slice it and unfold it, what you get is a rectangle. Because if you think about it, you could take a rectangular piece of paper or a rectangular piece of tin or whatever you have, and if you fold, like kind of curl it, you can create a cylinder, right? We do this all the time. We take a piece of paper and we roll it up in our hands and hold it. We're taking a rectangle and turning it into a cylinder. Now we want to do it with no overlap, of course, right? So if I do that, if I unroll my cylinder, the height of my cylinder is still going to translate over here. However, this right here, this distance, this length, that is going to come from this distance here. Right? The distance around the outside of my can, when it gets unfolded, turns into the length of this long side here. This distance is 2 pi r, right? That's a circumference. So this length is 2 pi r. So the area of my top is pi r squared. The area of my bottom is pi r squared. The area of my side is going to be the area of this rectangle, which is 2 pi r h. So 2 pi r h. Okay, so I said this on Friday, and I'm going to say it again because this is classic optimization. I've got two problems. One problem, I need to take the derivative of this and set it equal to 0. It currently has two variables in it. It has an r in it, and it has an h in it. That's not good. The second problem I have is that they gave me this restriction that it needs to be 1 liter, and I have not incorporated that restriction into this equation. Okay. We're going to do one move that's going to solve both problems. I'm going to incorporate this restriction in, and I'm going to do it by subbing it like system of equations style in for one of the variables. That way I eliminate a variable and I incorporate my restriction. Now it doesn't matter which variable you substitute, but let's use our brain. This equation has an r squared and an r, right? So if you solve this for r squared and then you're going to take the square root of it to solve for r, you're going to make a little bit of an algebraic mess. It only has one h, however, so probably our best bet is going to be to solve this for h and then sub over here in for h. That's what I'm going to do because it's going to make the algebra a lot easier. So I have 2 pi r squared plus 2 pi r, and then I'm subbing in for h, 1,000 over pi r squared. I'm also going to do myself a little favor and do a little simplification before I do some algebra. Okay. But again, notice what I did here. I had two problems. They're both fixed. I had a surface area equation that I need to maximize. I need to take its, or minimize, sorry. I need to take its derivative and set it equal to 0 and solve. And I'll do that. But first, I have to make sure it's only in terms of one variable. I also need to make sure my restriction is incorporated. I solved both of those problems by solving my restriction equation for one of the variables and popping it in. It's a pretty standard way to solve that problem. Okay, so let's see what we have here. I have surface area is 2 pi r squared plus I'm going to have a 2,000 pi, right? So 2,000 pi. Ooh, just kidding. There's a pi in the denominator that cancels. I don't even need that pi anymore. What? Okay. All right, so I'm going to have a 2,000. So 2 and 1,000, the pi's cancel. I have an r and an r squared. So I'm going to end up with a 2,000 over r, or 2,000 r to the negative 1. Okay, so this is my equation. This is the equation that I want to do calculus on. You may note we haven't done any calculus yet. To date, we have done nothing but a little bit of algebra and, frankly, lots of geometry. Okay, so this is where calculus comes in, right? This is my setup. We call this optimizing, and the idea is that you need to have a, quote, model for your situation. This is my model. This equation right here is the equation for the surface area of a can that has a volume of 1 liter. That's what this is. I shoved that restriction in over here. So all I have to do is minimize or maximize this equation. I'm going to optimize it. Okay, so we're going to take a derivative, set it equal to 0. So let's see. Optimize. It looks weird. Okay. Let's take our derivative. 2 pi r squared becomes 4 pi r. And 2,000 over r, which I like to think of as 2,000 r to the negative 1, becomes negative 2,000 r to the negative 2, or over r squared. And I need to set that equal to 0. So I'm not done yet, right? But this is my optimization problem. All I have to do now is solve for r. So I wrote my model, I took its derivative and set it equal to 0. Let's solve it. So for those of you who hate algebra, look what I can do. I have a 4 pi r. I can move this to the other side, 2,000 r squared, and do a quick crisscross applesauce to make this 4 pi r cubed equals 2,000. And then I'm going to go for my calculator because I know that r then is going to be the cube root of 2,000 over 4 pi. So let me just get that. 2,000 divided by, whoops, let's do that. 2,000 divided by 4. Yeah, I put that in my calculator. You bet I did. That's 500. Divided by pi, 159.15 decimal, I don't care, raised to the 1/3 power. I like to use fractional exponents. They're kind of my jam. Okay, so what I get is that the radius is equal to 5.419, The next decimal is a 2, so I'm not going to round up. And since I was careful with my units, I know this is centimeters. So I know the radius of my can now is 5.419 centimeters. Now, we have to be a little careful here with these problems and make sure we answer the question that they asked. They asked what dimensions. That doesn't mean just the radius. We also need to give them the height. So now that we have the radius, we need to go back and find the height that corresponds with it. Well, I have an equation for height right there. Right? So the height of this thing is going to be 1,000 over pi, the radius I found, squared. Again, I'm going to stress this number is a rounded number. In my calculator, the number I'm looking at is 5.419260701. That whole number that's in my calculator is what I'm going to use to do this calculation. So I'm literally going to keep it on my screen. It's still there. I'm going to hit squared so that it squares, my calculator squares that number. Then I'm going to multiply it by pi. And that's my denominator, which rounded is 92.263. But again, I'm not using that rounded number to make a calculation. I'm going to type 1,000 and divide it by that number. And if you don't know how to use the answer, I certainly hope you do, but if you don't, if you look above the negative key on the bottom right-hand corner of your white number keys, if your number keys are white, it's right next to the decimal point. Above it is ANS, right? And anytime you hit second and hit that button, it's going to call up the previous answer that you used. And so I'm going to type 1,000 divided by answer, and it comes out to 10.838. The next decimal is a 5. So AP will also accept 10.839. It will allow you to round up. Either answer is okay. So we have a cylinder that is 5.419 across, radius, and 10.838 high. It is worth noting that is basically a cylinder that has the same diameter as height, which is a little bit of a strange cylinder. We don't see a lot of cans shaped like that. Usually they're taller and thinner. Usually they're not as big around as they are tall. Or like a tuna can, they're short but wide. And every time I do this problem, I'm struck by that. I feel like maybe the people who make canned goods need to learn calculus. Like they could save some money on their packaging. But I don't, hey, what are you going to do? They don't care. Okay, so there's our answer. We're going to say that this can needs to have a radius of 5.419 centimeters and a height of 10.838 or 10.839 centimeters. Okay. So that is your constructing problem where they're going to just tell you, hey, build this. They might say build a box that has this restriction on volume, but what has to have certain dimensions or something like that. So you're going to see some problems like this. And again, in Schoology today, there is a practice problem. There is a section of practice problems. Again, constructing is station 2. There are some constructing problems, and on the next, if you scroll to the next page, there are links and there are answers and links to the full solutions. So I'm going to sign off for now because I've been talking at you for 19 whole minutes and you're probably sick of my voice, but don't worry, I will be back. See you soon.